So good day, this is my solution for the problem 6.5. Here, the simply supported beam carries two end couples, each of magnitude MO, but oppositely directed. So we need to find the location and magnitude of the maximum deflection if the moment or M sub O on the left support is removed. So for the free body diagram, we have here our beam with our length denoted as L and our bending moment, so we should it as M sub O over L. So here are two supports, and since the left moment is removed, we assume that the force on the right side would be greater than on the left side. So that means that our location of the deflection would be most likely nearest on the right side of the beam. So for our bending moment equation, we have our M is equals to M sub O over L times X. So here we need to find the integral of that. So we need to integrate it to find first the tilt of our beam, and for the second, for the shape of the deflection. So we have our flexural rigidity at the point of displacement denoted as V. As our first integration, we have moment over L times X. So that's going to be M sub O over 2L times X squared plus C1. So integrating that again, we get that M sub O over 2L times X squared plus C1 is going to be equal to M sub O over 6 times L. So that's our X squared is going to be X cubed. And then our C1 will be multiplied to X, and then our second constant. So to pinpoint the vertical displacement or the location, we need to set our boundaries. So first, we set our x equals to 0, and then our displacement as 0. So we get that 0 is equals to M sub O over 6L times x cubed plus C1x plus C2. So we set our values, that's going to be equals to, this one cancels, then this will be 0 as well, 0, 0. So this C2 is going to be equal to 0. And then for our second boundary, we still set our displacement at 0, but now we set our x as our L, our length of the beam. So to get that, we get 0 is equals to M sub O over 6L times x cubed again plus C1 times x, and then our C2 just cancels. That's, since our value here we have it as 0, and then that's going to be the values here would be M sub O over 6L. This is going to be L cubed plus this is going to be multiplied by L. So to simplify, we cancel that. We're left with M sub O times L squared over 6. So since we're getting the constant value, we set this to the other side, and then we need to simplify it again. So divide both sides by L. So we get M sub O over L is going to be rather M sub O times L is over 6 is going to be equal to our C1, and that's going to be negative. Since we set it on the other side, that's negative. Transfer that value to the other side, so that's going to be the value of our C1. And now since we have the value of C1 and C2, we can finally form our slope equation to find our value of x. So here we're going to use our first integration, which is the flexural integrity or flexural rigidity at displacement V is going to be equal to M sub O over 2L times x squared. And then since our C1 is negative here, it's going to be minus M sub O times L over 6. So we set that to 0 to find our x. So here we can cancel our M sub O. So since M sub O minus M sub O is equals to 0, we get that is equals to x squared over 2 times L minus L over 6. So to simplify, we multiply both sides by 6L. So that's going to be 6 over 2 is going to be 3. And then our L will just cancel out, so 3x squared minus, then we do the same on this side. That's 6 times 6, that's going to be 1. And then the L would be squared, since L times L is going to be L squared. Then we get that 3x squared minus L squared is equals to 0. Then we equate that with each other. We get that excuse 3x squared equals to L squared. So that's going to be equal to, so to get our x squared, we divide both sides by 3. So we cancel that out. So we're left with x squared equals to L squared over 3. Now we need to get the only value of x, so we get the square root of this side. So this will just cancel out, square root, and then we're left with x is equals to L over the square root of 3. Or if we put that in decimal, that's going to be x is equals to 0.577 times L. So this would be the value, or rather the location of our maximum deflection. So that's going to be here on this point. Now since we have our point of deflection, we need to find now the magnitude of the maximum deflection. So we can use that value here. Now we use our second integration. So that's going to be the flexural rigidity at point of deflection is equals to m sub o over 6L times x cubed plus c1x plus c2. And since we have this equation, we can substitute the values that we got from c1 and c2 again. So the value of our c1 is negative m sub o times L over 6, and then we multiply it by x, our value here, our variable x here. So we get that is going to be equal to, we need to simplify it, so we factor out the m sub o over 6. We're left with m sub o over 6 times x cubed, so we're left with x cubed over L minus L times x. So that's gonna be where we're gonna get our maximum magnitude. So to proceed, we need to substitute the value we got here, this one, the x, or the point of deflection. So we have here as L over square root of 3, square root of 3. So to get our maximum deflection, or magnitude of maximum deflection, so we set that up again. So flexural rigidity at the maximum deflection is going to be equal to m sub o over 6. Then substitute our value of L over square root of 3, that's going to be cube, over L minus, here we have our L again, multiplied by the same value of x, which is L over the square root of 3. Then we need to just simplify. So simplifying our numerator, on this parenthesis, we have our, since it's raised to 3, we can put that inside, distribute that. It's going to be L cube over 3 times the square root of 3 over L minus, so distribute the L inside, that's going to be L squared over the square root of 3. And then we can further simplify this. This one would cancel our L. We're left with L squared over 3 times the square root of 3 minus L squared over the square root of 3. Now for this one, we can, for the next step, since we have our common values of L squared over 3 we can factor that out again. So it's gonna be, they can join together here. So we're gonna be left with m sub o times L squared over 6 times 3, or the square root of 3, multiplied by the quantity 1/3, or 1 over 3 minus 1, since the value here is, we have 1 here, and then this 3, and then since this is factored out, it's going to be left as 1, and then our value would be 1 over 3 minus 1 is going to be negative 2/3. So if we multiply that to this side, it's going to be 1 over 6 here. So negative 2 over 3 over multiplied by 1 over 6 is going to be negative 1 over 9. So there we have our value of negative m sub o times L squared over 9 times the square root of 3. And since we have now that value, we can now divide both sides by the flexural rigidity. So we're gonna be left with, since this one is gonna be EI over here, they cancel, and we're gonna have our flexural rigidity on this side as well. And since it's negative, our final answer would be for the magnitude of the uh, maximum maximum deflection for our problem here. Magnitude of the maximum deflection of the moment on the left support, or rather the magnitude of the maximum deflection when the moment on the left support is removed, is going to be equal to m sub o times L squared over 9 times the square root of 3 multiplied by the flexural rigidity uh, on the downward direction, meaning it's from our beam, it's at point X, our maximum deflection is going down. So that's it, and thank you for listening.